we have energy transformations, and we have the idea behind the work kinetic energy theorem. So real quick here, I have it written up there, but let me write it over here. We've done problems that were called energy transformations before this, and they were basically looking at the energies at the beginning of a problem. Where's my pencil? Sure. And then comparing it to the end. We had some basic ones where you had a slide, and we knew we had, let's say, gravitational at the top and kinetic at the bottom. And we knew that all of that transferred to there, so we could set them equal to each other and solve. We had another problem on that same worksheet where there was like a spring-loaded gun where there was elastic potential energy, and then we could figure out how fast the ball was moving. So we had kinetic energy. We could set those equal to each other. We even had other problems where it maybe had a hill, and we had to figure out something about how much work there was due to friction, given a certain amount of gravitational and kinetic. So when I'm talking about energy transformation problems, I'm talking about what are all the energies we have in the beginning, and they could be kinetic, gravitational, elastic, or work, and then what are all the ones we have at the end, and we can set those two equal to each other. The other part is something that we looked more with the book homework, which was the work kinetic energy theorem. Basically saying if we want to speed something up, we have to do positive work. So you could do positive work to change this certain amount, which I have kind of written up there. We could do negative work, and negative work is going to slow it down. Or we talked about when no work is being done, we're not speeding it up, we're not making it go higher than it was before. So that one question where they had the paint can where positive work is being done lifting it up, how much work is being done just keeping it here, keeping it at the top? 0 because it's not speeding up and it's not getting any higher off the ground. And then going down, we were reducing the energy, so we have a negative change in kinetic energy. So as written up there, work is force times distance, and then final kinetic energy is that. And we subtract that because we always do final minus initial. So we'll have problems where we're kind of thinking about how much work we need to do to speed something up or slow it down. An example of one we need to do to speed it up is number 2, which we'll look at later. And this is somebody throwing a fastball. So we're trying to figure out what force is needed to throw, basically in this 2 meters of speeding it up, what force is needed so that when the ball is released at this point right here, it is traveling 44.7 meters per second, also known as 100 miles per hour. And then after that, we'll just do a review where we figure out how far it's actually going to go. So that's positive work. We're speeding it up. Number 3 is an example of negative work, because you have a bullet that strikes a block, penetrates, goes into the block, and the block is doing negative work to slow the bullet down. Also, type of work, number 4, is it's not dropping a rock, but you're throwing a rock downwards at 10 meters per second from a certain height. We could use our kinematic equations to figure out how fast it's going at the bottom, and if we did, we would actually indicate that it's going faster. So in reality, the final velocity down here is somewhere around 38 meters per second. So what in the world is doing work on it to slow it down? What type of friction? Air resistance. So we're having energy in the beginning up here. We have energy down here, but it's not the amount we started with, the amount we ended with is not the same. Well, where did it all go? It went in the form of this here. And then, well, like the first one and the last one, these are traditional energy transformation ones where we're literally going through the checklist of what are all the energies we have at the beginning. Okay, it goes through. What are the energies there at the very end? So that's why I kind of split it up between what am I talking about when I say energy transformation. It's sort of these pictures right here where there's a beginning and end, and which ones are the work kinetic energy theorem. They basically are mentioning something about force. So something to add to here, up here, is the checklist of how we know we have in each of these. So is it moving? Okay, if it's moving, then we have that. So we're going to write these up here it is up there as well, but here. Okay, if it is moving, then it has kinetic energy. Is it at a height greater than 0? If that is the case, there is gravitational potential. Is there a spring? And then in terms of this right here, basically, does it mention specific work being done? Sort of like the baseball player is speeding it up, or the block is slowing it down. Whereas these ones over here are specific, this one there and that one there too. Is there friction? Because friction can't speed you up, it can only slow you down. So far. As I said, the Mario Kart speed strip would technically be a friction patch that could speed you up, but there's no such thing as that yet. What do we even look like to do that? Okay, so we're going to look at this first one here, and although we observe a child on a sled and it's going to compress it to a spring, we also saw last week that it doesn't matter the shape of this here as long as there's no friction, and there's no mention of friction here. So to kind of help me, instead of looking at the whole thing and only concentrating the beginning and end, I kind of like to put a dotted line down the middle just to say, hey, the left side is independent of the right side. And then we have to go through and identify which energies do we have. Is it moving?
Yes.
Yes, it indicates it's moving right there, so we have kinetic energy. Is it at a height greater than 0? Also yes, so we have gravitational potential energy. Is there a spring? There is a spring at the end, but there's not a spring at the beginning, so that's why the dotted line kind of separates that. So no elastic, and there's no mention of work being done. Basically, if it was like, they'd be almost like a bobsled, like, hey, somebody's applying force over a certain distance to get it moving, so there's no mention of that being, that happening. So those are the energies we have at the beginning. At the end, it doesn't say this here, but technically it should be, that should be H equals 0. It is not moving because it's compressed against the spring, so we have no kinetic. It is on the ground, so there's no gravitational. There is a spring, so we do have elastic. And there's no mention of any friction. It'll be very clear to say, hey, there's friction in this problem. So no mention of friction. So all the energies, if these two combine to 100, then that means all of it has to go into here. And so what we can do is we can just set those equal to each other. Conservation energy, we can set them equal to each other. At this point, it is a plug and chug matter. Now, for the sake of me and writing out your work in order to get as much partial credit in case anything goes wrong, write everything out with just the equation, nothing plugged in, and I'll show you the hardest part in these problems. Okay, we've done that. Hardest part here, let's see if I can do it. First try. Oh, there we go, yes, just like that, yes. The squares, and I know I've done that before, but why do I make it a big deal? Because that's usually what I find. If I put it into your mind and said, oh, you keep saying something about the squares, maybe people will remember it. So this is 1/2 k times x, also squared. Because on the test, I'm not going to give you 30 of these. I think I gave you 2. Yes?
Why can you say, like, what makes it so you can set those two things equal?
Conservation of energy. So we're not losing any energy due to friction or heat. If we were, like, even if we were losing energy here, if there was friction here, we would just have that right there. We would have a work due to friction. But there's no, you cannot create, you cannot destroy energy. You can just change its forms. So that's the reasoning behind that. Okay, so now we got to plug in the numbers carefully so we don't. So take your time. Even though we put the square there, we need to make sure we actually do it in the there as well. Because when I go through here and I grade, I'm like, okay, do you have the right energies? Did you write the equation correct? Did you plug in the numbers correct? That's sort of what I'm looking through. Height 24.
Right off the bat, can you just cancel that out?
No. So, well, 2 reasons. Mathematically, you can't because there's not a 1/2 here.
Oh, yeah.
But also, don't cross out any 1/2s. Don't, because if, let's say I wanted to ask you, okay, once you complete this, how much energy was there in terms of kinetic, and you were to get rid of this 1/2, mv squared is not energy. 1/2 mv squared is energy. So just keep everything like it is when you're going through there. Even if there's an m or a mass and everything, just keep everything in. Don't cross anything out. So what are we trying to find? We're trying to find what is the spring constant. Basically, how stiff or how loose does the spring have to be in order for it to compress 3 meters and come to a complete stop. So a reminder that spring constant is Newton over meters. So how many newtons is it needed to compress? or stretch this certain spring 1 meter. Even at this point, take your time writing out what these energies are. So as we're going through and calculating this, we can see that a vast majority of the energy is coming from the fact that it's at a height of 24 meters and at a mass, and just a measly 200 joules is contributing to the total energy in the beginning. But it is still contributing some amount, and we need to take account of that. I said getting used to writing the workout here, because saying, well, I can do it all my calculator. Well, congratulations, but you need to actually show this, because when we get to our next chapter, we're going to be doing conservation of momentum, which the equations can get quite long. To give you an idea, conservation of momentum, one of them is m1v1 I plus m2 v2 I equals m1 v1f plus m2 v2f. And you have to write all this stuff out. Or even the conservation of kinetic energy, which I'm not going to write out, but basically is 1/2 that squared, 1/2 that squared, 1/2 that squared, 1/2 that squared. So even though the equations are long, the mathematics is not that hard as long as you're not trying to do too much. So this spring, I don't know how basically saying it takes this amount of newtons or force to stretch it a meter. So now that we know this, if we had any spring that was stiffer than this, then it would come to rest before 3 meters. And if it was any looser than this, then it wouldn't compress all the way and would hit the wall. Part 2 of just discussion here. After the spring brings the child sled to rest, let's imagine that it then pushes the child sled combination back to the left. How fast will the child and sled be moving when it arrives back at the height of 24 meters? There might be a hint here in how much room I gave you for work, as opposed to how much I did before. The idea of conservation of energy, what are our predictions? How fast will it be going? It comes down here, compresses, and then it fires it back up the hill. If there's no loss of energy, how fast should it be going? It would have to be going the same speed, because here's the thing. If the combination of kinetic and potential energy led to this specific spring has to lead to the same potential energy and kinetic energy combo. So yes, when it gets up to the top of the hill, it will convert that much energy into that, but we still have 200 joules left over, and that comes from the fact that it has a speed. So if there's no loss, there's no friction, there's no loss of energy due to friction, then as long as everything is kept the same, and it doesn't even matter if the track were to change, if the track were to become steeper, as long as it goes back to the same height with the same mass, the velocity is going to be the same as it was before because of conservation of energy. Okay, if there was any kind of friction, then it would be less than that, or may not even make it up to the top of the hill. And you could plug this in. You would just have 1/2 times this here. You'd have the same height, and you would calculate, and the 2 would be there. Okay. Let's look at an example of a work kinetic energy theorem description here. So we have a pitcher who, from the beginning of the throw to the end of the throw, estimating about 2 meters. And we're trying to figure out what force over that 2 meters is needed so that when the ball is released 2 meters later, it's now traveling 100 miles per hour or 44.7 meters per second. So this is, I guess you technically could call this an energy transformation one, but what we have here is we have work equals change in kinetic energy, and we're using that equation that we have that is up on the board we wrote on the other page. So force times distance, 1/2 m VF squared minus 1/2 mvi. It's always final minus initial. That's how you get the difference between that. And we'll observe here that we're basically given everything except for what we're trying to figure out. It says the mass of baseball is 0.145 kilograms, which I looked up, made sure that was right. What is the initial velocity of this pitch baseball before it is brought to 100 miles per hour? It is 0. At the back of the stretch, it's 0, and then through 2 meters, it is getting to 44.7. So that right there is 0. You could also, you could just say, another way of thinking about it is that the amount of work that we have is being converted into kinetic energy. However, this also allows us that what if the ball was moving in the beginning before it got sped up? So yes, all the work that's being done by the baseball player is being converted into kinetic energy, but this is another way of writing this out. So we're looking at the change in kinetic energy. So we're also given the distance, and we're given the final velocity here, which is 44.7 meters per second. The only thing that we don't know is exactly what we're trying to find out. Nothing's nicer than that. Like I said, to be clear, yes, you could just think about, okay, what are all the energies we have in the beginning? But we're not really, although it's at a height here, we're not changing the height, so we don't have to take into account how tall the player is. We're just looking how much force is needed by the pitch to get to that specific velocity. So the force, that's what we're trying to figure out. I guess I can do it up there, do it down here. I'll do it up here. What? Yes. Because here's the thing. We're looking at this. This is the problem right here. This is the whole entire problem. What happens after that is the review question, projectile motion. So it starts at 0. It ends at 44.7. It does that through a distance of 2. We're trying to figure out what force is needed over that distance to allow it to have that speed. Basically, what force is needed to cause the amount of work that we need to speed it up. So 44.7 squared. You could just recognize that that goes to 0 if we wanted to be official and write it out. And since it's increasing its kinetic energy, it's increasing its speed, that would be a positive work. The force is being applied in the direction that it's traveling. It's speeding it up. I mean, think about it here. The baseball is moving this way. The force is being applied is also this way. We talked about those are parallel to each other, then it's positive work. The kinetic energy of this 44.7 squared times 0.145 times 1/2 is 144.86 joules. So how much work is done? 144.86 joules. How do I know that? Because that's the increase in kinetic energy, but the force needed is 72.43 newtons. This doesn't seem necessarily like a lot. I'm trying to think about how much 100 newtons is to pounds. But the reason that the force does not have to be some insane thousands of newtons is because the baseball player has a distance of 2 meters to slowly accelerate over that time. If the baseball player had instead only had, let's say, a foot to accelerate from 0 to 44.7, you can guarantee that that force would be enormous if you had to do that. So the longer time, you think about when you're in your car and you're speeding up. If you have a longer distance that you have to do to speed up to a certain speed, then the less force you need. If you want to go from, if you're trying to take, if it takes you a quarter mile to go from 0 to 60, if it takes you a quarter mile to go from 0 to 60, you have a really bad car. But let's say that you wanted to go from 0 to 60 in 100 meters, you would need a very, very powerful, forceful engine. If you wanted to go from 0 to 60 in 10 feet, you better need an explosion that will just explode you to that distance. So the increase in distance, 2 meters, which doesn't seem like a lot, is enough to get it to that speed. Now we're going to do a review question. Because we never had a final exam, we never had a final exam review, you never had to think about this ever again. We're going to try to figure out if the baseball player just throws exactly horizontally at 44.7 meters per second from a height of 1.7 meters, how far does he throw? We're not finding how far the pitcher's mound is to the plate. Anybody in baseball here would know that distance?
60.
It's like 60 feet 6 inches. I think somebody 60 feet 6 inches. This could be more than it, could be less than it. So I'm gonna help you out here. Whenever we did this before, we always started with our good old T-chart to figure out what was going on. So what are we trying to figure out? We're trying to figure out what is that distance. If you could throw 100 miles per hour, how far would the ball travel before it hit the ground? We had Vx, we had delta x. This is an example of a type of problems that sometimes appear in the AP Physics homework where they're called review problems. And you know this because it's ultimately going to have what you were just working on and then every iteration of something that came before that. So forces had projectile motion. Work and energy had forces that led to projectile motion. Momentum had something related to energy that related to forces that related to projectile motion. So you do it so many times that when you get to it, like in second semester, you're like, projectile motion, this is really, really easy. So it's just a barrage over and over and over again. Now, if this is greatly simplified, but the fact that this is released completely horizontally. So what is Vx? What is velocity in the x direction right at the release of the throw?
44.7.
Good, 44.7. You can think 44.7 cosine 0, but this is 44.7. We were trying to figure out delta x, and we don't know time. So we don't have enough in the x direction. We don't yet cry ourselves to sleep. We go into the y direction next. The initial velocity in the y direction, because it's completely horizontal, is 0. Now here comes to the part. The height is 1.7. What is delta y? Negative 1.7. Awesome. We don't know the time. Gravity. Gravity is going to be negative. Why? Because we have direction with these. There's the projectile motion, free fall, we always negative. Now, the way we used to do this, like there was a way we just brute force method did this, where we said that this was the first, the second, the first, the second, the third, the fourth. To find time, we used to use the fourth equation, find this, make it negative, plug it into the second equation, find time. But because VIY is 0 here, we don't have to do that method. This third equation, we stayed away very, very far away, because if we needed to find time, what would we have to use? Which formula? You'd have to use a quadratic, and we didn't want to do that, so we did the fourth and the second. However, VIY is 0, which means that right there is 0. So to simplify this, because VIY is 0, we can use the third equation to solve for time without having to use the quadratic. Why? Because all of that goes to 0. We have delta y, we have gravity. Go ahead and solve for time. Because once we find that time, that is the same time in the x direction. This is not one where it's going up and going down. We need to multiply times 2. Whatever the time it takes to fall 1.7 meters is the same time it takes to go sideways. I believe I got a time of 0.59. Concur with anybody, the time here. Multiply by square root, take the square root. Okay, 0.59 seconds. That is the same time here. It is traveling 44.7 meters per second sideways for how long? 0.59 seconds, so we can multiply both of these. And we actually get a horizontal distance that's much further than the distance to home plate when you convert to feet. Uh, 26.37, I believe. Which last class we calculated as 86.5 feet, which means that it's going much further past where the catcher would be. So if this was a picture up here, likely if the pitcher was there throwing 100 miles per hour, the catcher may be somewhere here. Pitching is a lot more complicated than just throwing something at the maximum height. I mean, there is, so you say, well, would that be a strike or would that be a ball? It's a little bit different because you know that it's going to drop a certain amount. But this was just a review to figure out how far it was going to go. And we successfully did that.